So welcome everybody. I'm so glad to see all of you today on a Friday afternoon. My name is Cindy Lin, and I am a community fellow for the ESIP Machine Learning Research Cluster. I'm currently a PhD candidate at the School of Information in University of Michigan, and soon gonna transition to a postdoctoral fellowship in Cornell. And we are very happy to have Tom Augspurger. I feel so sorry whenever I can't pronounce somebody's last name correctly, but I hope I did that a good job. So Tom, as some of you might already know, is a software engineer currently at Microsoft AI for Earth, where he's working on the Planetary computer. He's worked on various open source libraries like Pandas, Dask, and has been involved with the PanGeo community. And today he'll be talking about scalable geospatial analysis. Off to you, Tom.
Alrighty, thanks. Okay, let me swap this. All right, hopefully you can see the slides now. So we'll start off with some slides at the beginning and then get into a demo. Yeah, so I'm gonna bring up the chat here actually so I can see that. Great. Yeah, so today I'll be talking a bit about what we're doing with the Planetary computer and then going through some an example that kind of shows why we're building that. Yeah, so I'm on the AI for Earth team, where we are part of Microsoft's conservation and sustainability organization. And what we're doing, my team, the team working on the Planetary computer, we're trying to make it possible for people to succeed in doing their geospatial and sustainability work on Azure, whether that's like research or planning or policy making. We want them to be able to succeed when they're trying to do that on Azure. There's a few components of the Planetary computer that kind of make it clear exactly what it is and isn't. Kind of the core of it is like a ton of data, a lot of geospatial data in blob storage on Azure. So these are mostly public sector data sets, things like Landsat and Sentinel are there in Azure in analysis-ready cloud optimized formats. But it's not just remote sensing data sets. There's like the USDA's forest inventory analysis, a big set of tabular data sets, weather data sets, output of climate simulations, things like that, all in Azure in cloud optimized formats. So that's like that's like publicly available data with a slight asterisk on like we throttle it if you're accessing it anonymously, but that's public sector public data. Just having those like bits on blob storage is like a lot of effort to get them there. But it's not like the friendliest, most user-friendly way of using the data, of exposing the data. And so that's why we're embracing this new standard called STAC. It's the Spatial Temporal Asset Catalog. It's this structured way to describe these types of spatial temporal data sets. That lets us do things like build HTML websites, catalogs based on those data sets to show you what data we have available. It also allows users to like search for specific items from those data sets. And we'll see that in action in just a bit. And then taking some lessons learned from like the PanGeo community, we want to make it easy for people to get started exploring these data sets. And so we have a Jupyter hub where people can, once they get an account on the Planetary computer, they can log in and they are there with an environment that has hopefully all the packages they need to do their work, and they can just really quickly get going computing on the data in a cloud optimized way. So the data's in Azure, and then we get them a compute environment in Azure as well, very easily. And then if they need to scale out to larger data sets, then we have that Dask gateway hooked up to that Jupyter hub so that they can distribute their computation on a cluster of machines. And again, that's borrowing very heavily from the PanGeo approach. And then, also kind of in the vein of the PanGeo approach is like, we'll be seeing each of these. And the most prominent is definitely the compute. Like I'm logged into the hub right now. You're going to be seeing that. But it's worth emphasizing that like you can swap out the compute with your own compute very easily. You just want to make sure that it's in the West Europe Azure region so that you get full unthrottled access to the data. So that's worth keeping in mind. Okay, so first thing I want to talk to, and if you do have questions, just put them in the chat throughout. I've got the window up here so I can take a look. First thing we'll be talking through is STAC, the Spatial Temporal Asset Catalog. So if you have like a question that you want answered, you're typically going to be going through a thought process like, I need to answer this question, I need some data covering some region that you're interested in over some time period. STAC makes it really natural to be able to answer that question. So for example, you need data from Landsat 8 collection 2 level 2 covering some bounding box here over 2016 to 2020. If you just had like files and blob storage, you could probably come up with the right files that match that query that that you have in your head, but it's not the easiest. Like there is some structure here in the URL paths, but yeah, you have to kind of know exactly like what these numbers mean. I think they're like where the satellite is over the Earth. I'm not entirely sure. There's a date in here somewhere, so you could figure it out, but it's pretty challenging, especially if you're not like intimately familiar with this specific data set and its naming conventions. And that knowledge doesn't really transfer over to any other data set like Sentinel or NAPE or things like that. So that's where STAC comes in. It's this way to consistently describe these data sets. So it doesn't matter if it's Landsat or Sentinel or whatever. Doesn't even have to be a remote sensing data set. It's a way to consistently cover the data and let you do things like build HTML catalogs, which we'll see in a second, and also build like these clients to query the data and these endpoints to serve those clients' requests. So in this case, we're going to be going through our little story here. We'll connect to the Planetary computer endpoint. Again, that's publicly accessible. You don't need to have any credentials or anything like that. We'll connect to that endpoint and then go through our little story of, I want this data, Landsat 8, covering this bounding box over this time. And I want to get those back as some items. Okay, so that's a way to very quickly go from the many I don't know, tens, hundreds of thousands of images, files that compose Landsat, down to just the ones that you care about for your question. So let's jump over to the demo now. So in this demo, I'm actually, how does the font size? I'm gonna try this font size. I want code font size, I think. I don't know if that did anything or not. Yeah, maybe a bit bigger. I'll try this. Let me know if it's too small. So we're going to be going through this kind of like story here, where we've been tasked with taking, looking at how land use has changed over 4 years in for this region over Maryland, and kind of try and look at what's changed over the 4 years, basically. So to do that, we'll be using various components of the Planetary computer. So I've logged in here to the hub, and I did that ahead of time. It takes a little bit of time for these GPU profiles to scale up, since we don't leave them idling around. So we're going to be, we've logged into this hub here, and then we're going to be using the STAC endpoint to discover some data, specifically NAPE data that's hosted in the Planetary computer. If we open this up, we'll go to the specific data set here. So this is the NAPE data set, where we can view all the properties of the data set, the various bands that are available, things like that. And there's some example notebooks here if you want to get started. Okay. So we're going to be using this NAPE data set, and the problem we've been assigned is to take this pre-trained model. So we're not doing any training here right now. This is just applying some pre-trained model to a bunch of data in parallel on a couple of machines, where each machine has a GPU. Okay, so let's see here. Yeah, so since it is a fairly large data set that we'll be working with, we're going to handle that scale in a couple ways. So first of all, cloud native workflow, just fancy way of saying the data's in Azure Blob Storage, the VM's going to be running in Azure in the same region. So we have a nice high bandwidth step, high bandwidth connection between those two machines, and we're going to read data straight from Blob Storage into memory. And then we're also going to use a cluster of machines to do the computation in parallel because it's cool, or you could wait around a bit longer and avoid all the headaches of distributed computing. I'm going to restart this here just so I don't get a timeout later on, which happened to me last time. So, okay, so in this case, yeah, distributed computing is challenging. We are using Dask Gateway to make that a bit less challenging for users. So as a user, if you want a cluster, you'll connect to the gateway that we've configured ahead of time and then customize your cluster slightly. So in this case, we're going to ask for a GPU, we're going to ask for sufficient memory on the workers, things like that. And then we'll scale that cluster up and connect to it to get our client. And you can see that we have our 2 workers here now. And I'm going to open up the Dask dashboard by pasting it here. So for those of you who aren't familiar with Dask, basically it's a library for parallel and distributed computing in Python. And then lots of different libraries like Xarray will use Dask to do computations in parallel on chunks of data. I'm going to open up a couple of windows here. We'll get the, what do we want? Test stream and the progress. This will give us an overview of what our cluster is up to as we go through the computation. Okay, this chunk of code isn't doing anything special. It's just downloading the pre-trained model that our teammates on the AI for Good team put together, downloading it from blob storage locally, loading it in. So it's a PyTorch model, specifically using the segmentation models PyTorch package, and then loading it into memory. And eventually we'll scatter it out to the workers. But I have no real idea what this model does, how it works. It was put together by Caleb Robinson and his team from the AI for Good team. Okay, next thing is the data discovery. So I kind of previewed that earlier on. In this case, we're going to be looking at this area of interest over Maryland. It covers, I can try it. This is probably bad as yeah. I need to Jupyter, can't spell, lab GeoJSON. I need to install this package for that to render. Let me do that real quick. I'm using an, this is fixed on our staging basically. So, but I'm running on the production version for the demo. So this will show the actual area of interest here now. Sorry about that. Okay, so we're looking at this area over Maryland, and you can zoom out a bit so you can see where it's at. So this is the area that we're interested in. And within this area, there's a few hundred. Let's go ahead and do the query here. So I'm going to make a request to the non-staging endpoint here, to our STAC endpoint. And we're going to do a couple of searches. So we're going to do a first search for 2013, and then a second search for 2017. So these are all the NAEP scenes that cover this, these 2 searches. And there's 440 and 443. So you can see it pretty quickly found those scenes matching our query. For those of you not familiar with NAEP, it's a data set of aerial photography that's collected by the USDA. It's pretty high resolution. I think it's like 1 kilometer or maybe a little lower now. But the revisit rate is something like 3 years, I think. I could be wrong about that. But so it's a high spatial resolution, but not as high temporal resolution. Okay. So now we have a bunch of items that match our queries. So if I go like search 2013.items, look at what one of these items is. So it's this PyStack item. It has a whole bunch of information in it. So one of the things, I think it's image, is a link to the actual URL in blob storage. So this is the, I had like that long list of files in blob storage. This is one of these. And like, that's great that we're able to quickly find that. There's a bit of an issue with, I mean, I can do it here real quick. If I import rasterio to actually open up this file, this will take a bit of time. Like a second or so, yeah, so a quarter of a second just to open the file, and this just gets like the metadata of the file. And so if we have, 440, like almost 1,000 of these across the 2 years, that quarter of a second kind of adds up if you want to work with those. So there's a couple of libraries that are basically exploiting all the rich metadata in these stack items, things like the projection information, the shape, there's a whole bunch of other stuff, specifically like the transform for rastereo, that tells you exactly where the data within lies. And so basically what we're going to do is construct an X-ray data array from that metadata without opening up the actual data. Yeah, I might have been off on my spatial resolution. If I open that up, I think we say here, yeah, 1 meter, only off by a factor of 1,000. So this is also why it's nice to have these catalogs. You can easily check that. And I think the 0.6 meter is like the newest data set, like 2020. I could be wrong about that though. Okay. This is going to be using a library that we made called StackVRT. I'm actually going to kind of caution you that you might not want to use StackVRT. There's another library called StackStack, stack.readthedocs.io. It takes like a really, really cool approach. It's like very focused on X-array and Dask. StackVRT, anyway, I would recommend using Stack if you're going to be taking these stack collections and constructing an X-ray data array from them, then I would definitely point you towards StackStack. The only caveat is that it doesn't currently work with multi-band cogs, which is what we happen to be using here. With Nate produces multi-band cogs, so that's the only caveat. But I think it's a more powerful approach than StackVRT takes. So anyway, they both have the same sort of ideas. Use the information that's in these items to construct data arrays. They just go about it a bit differently. Okay. But the basic goal right now is to construct this X-array data array. So if you're not familiar with X-array, it's an n-dimensional array for Python that can be chunked along one or more dimensions. And then the key thing is that it's labeled dimensions. So in this case, we have a data array, a four-dimensional data array that's indexed, has dimensions time. So we have our 2 time periods, 2013 and 2017. Band, so red, green, blue, and near infrared are the 4 wavelengths captured by these cameras. And then Y is longitude and X is latitude, so in the vertical direction. And then that full data set, so this is 175 gigs in total, broken into chunks of 270 megabytes each. So that's the full data set that we're working with. Again, using StackVRT and rastereo to do like the alignment to make sure that that the 2 time periods are all lined up with each other, basically, so we can compare pixel values. Yeah, so I'll leave it there. If there are any questions, let me know on that. There's one. Yeah, example notebooks. Yeah. I'm really happy with those example notebooks specifically. And so at the end, I'll show you where to request access, basically. But this launch in hub button is really nice. It'll take you straight to the hub, to that notebook. Okay. So we've got our big data array, and remember our task was to compare land use in 2013 to land use in 2017. The model that we're using needs a bit of pre-processing done to it, so we're gonna go ahead and do that here. We're gonna subtract the per year mean and divide by the per year standard deviation, so that's this normalization step here. And then just because I don't understand PyTorch, the model had some issue with chunks that were not divisible by 32. So we just chop off like the last 17 pixels or so in the bottom right corner. I'm sure you could fix that, pad it or something. I just decided to chop them off, but not super important. Okay, now hopefully our workers, our workers should be online since I scaled them up ahead of time. I think when I refreshed the page, I lost our dashboard here. So I'm gonna scroll back up and get the URL here, cluster client.dashboard link, dashboard link. And I'm gonna paste that in here. Sorry about this. Okay, there we go. Okay. Sorry about the scrolling. Okay, so all we've done now is scattered our model out to our workers. So basically the approach will be, we have our model on our workers, they're gonna pull down some data, do the prediction, and then store that out on the cluster. Okay, the main thing we worry about here is oversaturating the GPU. So these chunks of the data set, the whole data set's really large. It's like 180 gigs. Even the chunks of like 250 megs are a bit too large for the GPUs that we're hooked up to. I don't know exactly how much memory there is, but between the model and a big chunk of data, it ends up often oversaturating the GPU. It runs out of memory and complains. So what we're going to do is basically break it up into even smaller chunks. So right now we have our big data set here with these 270 megabyte chunks. We're going to break those into even smaller chips, I guess is the common name for them. So that's done here is we're just going to make this even smaller here. Iterate over each of those chips and then do the prediction on the GPU. So that's kind of the core thing here is we take out a little slice of the chunk, copy it over to the GPU, do a prediction for it, which happens really quickly on these GPUs, and then copy it back to the host memory. So it's a bit convoluted, but this ended up giving pretty good performance. We were able to keep the GPUs reasonably well saturated. Okay, one thing I forgot to mention when I was talking about Dask is it's lazy. So when we loaded that data set in, the 180 gigs, it returned instantly, but that's because we didn't actually load any data. All we did was look at the metadata from the stack items. So now we've done our predictions, and again, it was like instant. We mapped this function. We're calling this function on each block. It was instant because again, we haven't actually done anything. We're just manipulating the metadata. To actually get a result, you have to call compute or do something that consumes the data, like plotting it. And so this will actually kick off the computation. So right now it's doing things like reading from blob storage. That takes like 14 seconds or so. You'll eventually see the normalization. It's all been fused together, but this is where it's doing the normalization step and the prediction step on each of those chunks. Okay, so that's like a bit of the data. Yeah, so the question was, is Dask supporting deep learning libraries like PyTorch now? This is still an area that's like a bit confusing because libraries like PyTorch, TensorFlow, they have their own distributed runtimes. And it's not exactly clear what the best way is to kind of like marry those two. So like Dask has its distributed stuff. PyTorch has its own distributed stuff, and like how do those talk to each other? I think there's like a lot of interesting exploration in this space currently. What I'm doing here is like the simplest possible thing from the point of view of a Dask user. Okay, so I'm being very explicit about, hey, I'm taking, I have just a regular Dask array. It's host memory. I'm very explicitly copying it over to the GPU here, and then doing the prediction here. So like that's kind of it's regular Python code. I'm not doing anything here with like Torch's distributed runtime. I'm just using Dask and then manually passing data from the host to the GPU. Long story short is like I think people are still figuring this out. There's a good talk yesterday at the Dask Summit by the Light GBM. So Light GBM's this gradient boosted tree library that has its own distributed runtime again. And they went into some of the details about how Dask and LightGBM work together. It's a good way to think through that kind of issue of how do these two distributed runtimes talk together. So I would recommend checking that out once it's uploaded to YouTube. It was just yesterday. But I don't have like a super clear example of like, this is the way to always do things. Okay, right, getting back to our actual scientific result of interest here. Where is land use in 2013? Where does it differ from land use in 2017, at least according to our model? So that's going to be this change variable here. It's a Boolean. If that's true, then the pixel has changed over the 4 years. Or not the pixel, the classification of that pixel has changed over the 4 years. We're going to mask out the values where there's no change just for some visualization later on. So a value of 0 means no change. And we can look at an array of these again. Similar sorts of thing, except now we're just doing this masking after the fact. To kind of explore how the model is doing, I'm going to get rid of this. Sorry, I was debugging this earlier. Going to select out a chunk of data somewhere in the middle of the data array. So the big 180 gig data set. And then go ahead and bring back some results locally for visualization with HoloView's HVplot. I'm going to get the raw data itself, so the actual imagery coming from the planes, the predictions, and then the masked out predictions, the changed predictions. That's going to be loading it up here in the background. Hopefully as it's stalled, we'll see. Oh, it's not progressing. It's a little concerning. There we go. I think it was just taking a while to read that chunk of data. I do need to do some profiling of why some chunks take so much longer to read than others. I'm not actually sure what's going on there. But yeah, we'll see. Most likely just saturating the bandwidth of the machine from blob storage to the worker. Who knows? Okay, so that's going to finish up here soon. We'll bring it back locally, and then we've got this little HoloViz panel dashboard in the notebook. This is the screenshot of what it'll look like, so I'll explain the layout here. So we'll have the 2013 images on top, so we'll have the raw imagery, and then the classification according to the model for the pixels in 2013, with the no change to 2017 masked out as black. So black is no change. And then on the bottom, we have, again, the raw imagery, this time from 2017, and then the classification in 2017 with no change masked out to black. So this is just rendering it right now, hopefully. And it'll come up. And then since this is hollow, I'm gonna make this a tad smaller so that it fits. Since it's HoloViews, it's nice and interactive. And as we like zoom in here on this area, you know, we can see a section that's changed, and the full resolution comes in because this was developed over the 4 years. And you can pan and zoom around, get a sense for how your model's performing on the various classes and the various kinds of land underneath. It's a nice way to kind of debug it. And then when you're ready to, you can kind of scale out the predictions. So that was just on a small subset. You can scale out the predictions to the full data set. So what we did earlier on was did it for all of the Chesapeake Bay watershed, and then wrote those results out to blob storage. And at that point, you kind of have like an application built on top of the Planetary computer. Is kind of the idea that would be appropriate for someone like a someone who doesn't know Python but is comfortable interpreting the results of these geospatial outputs, these models, like a conservation land use planner, things like that. Okay. I'm actually going to kill that so that it scales down in the background. Okay, that's that. Yeah, so if you're interested in learning more, the URL to where you can go to find out more is this planetarycomputer.microsoft.com. Like I said, there's a request access form here. when you do request access and get approved, you get a bit, but not much. So first of all, you get access to the hub. So that's a place where you can go and you don't have to worry about managing your environments or anything like that. But all the data itself in our catalog is publicly accessible. You do just need to sign your requests. And in our documentation, we have an example well, we have examples, but also why we do that and how to do that. So that's a good way to get started, is you can get access to the data, even if we don't get around to approving your account for a little while. Great. I think that's it for me. I'm happy to take questions now. Yeah, thanks for listening.
Thank you so much, Tom. That was a very fantastic talk. So the floor is open. Anyone want to ask a question? You can go ahead. You can unmute yourself and just ask. Okay, I have a question about today. So what exactly the Planetary computer offers? Like data catalog and Jupyter Lab? Is that?
Yeah, I think that, and then the STAC API. So depending on how you're accessing the data, the STAC API is actually my favorite part, just because it makes it so easy to find the subsets of the data that you care about. Yeah, those are the main things. And then again, I want to emphasize, like, the hub is nice and convenient, but if you want to do like really continental scale stuff or whatever, the hub will only get you so far. So in that case, it's easy to swap out the hub for your own compute deployed in Azure. If you already have like a whole pipeline set up in Azure, just make sure it's in West Europe, and then you get the full access to the data.
You mean the data in the? Okay.
Oh, sorry, Jensen. Yeah, excuse the maybe naivete of this question. So just differentiating, because I know this is like in the vein of Google Earth Engine competitor, and what would make this an attractive option in terms of accessing your own data, linking this with Azure or other compute resources. I mean, is that any special sauce in there? Can you speak a little bit to how this would integrate with your own resources that you've built out?
Yeah. I should say up front, like, I'm learning geospatial. I'm definitely not an expert. I've never really used Google Earth Engine other than just playing around with it. But like, my understanding is like it's like this extremely nice way to do your work. But it is like you're using Google Earth Engine start to finish, and like it hopefully has everything you need. If it doesn't, it might be a bit hard to extend. Again, with the caveats that like I don't actually know how Google Earth Engine works. From like a scalability point of view, I think like Google Earth Engine, it has its own way of doing it. It does the distributed computing for you on like a big MapReduce cluster or something in the background, so that you don't have to worry about it, but you also can't worry about it. You can't really control it. And so if you wanted to swap out, say, use the Google Earth Engine API to find the data, and then like use your own cluster of machines to do the compute, that's not really possible, I don't think. So that's one place where, again, if you have your own compute in Azure, or if you want to do something with like Azure Batch rather than Dask, then again, as long as you're in West Europe and you're not moving data across cloud regions, then it's going to be fine, because there's nothing in here that is specific to the hub. Actually, yeah, the only thing that is specific is that we automatically set an API key when you create this client. That's it. So you just need to manually set like the environment variable to make sure that's working. But other than that, like, yeah, the idea is to be able to swap out like any of the components for your own stuff. aside from like, you don't want to host all of Sentinel yourself. Hopefully we already have a copy of that. So yeah. And then I should also say, like, you mentioned specifically like bring in your own data. Like, we don't have a good story for that right now. Like, it would essentially require you to, if you wanted to use your own data in the exact same way we used NAPE in this example, you would need to have stack items cataloging the metadata of all the data, of all your data as well. We want to make that easier, but we're not there yet.
All right, that seems like something that as things roll out, people will get to play with a bit. And I'm sure a lot of people in our community will be interested in that topic. So thanks so much.
Awesome. Looks like there's a question from Jonathan. Yeah, so ideally everything, so this tutorial is mostly copy pasted from here. So this is the docs/tutorial/land cover. And this also, yeah, it's on GitHub as well. So if you want to take a look at the actual notebook itself, it's there. And so, yeah, with that, you can adapt it while, until we can get to approving your account. You can play around with it, see how it works. The one thing that might be kind of hard is I guess you didn't see it. When I started up the server, I selected an environment. This is like a very specific environment. It's kind of hard to get all of these packages installed at the same time. So we're going to try and get those that environment open sourced as well. Just haven't gotten around to it yet.
I had a quick question. We have data, spatial temporal data already stored in Elasticsearch. And on top of that, we have a in-house REST API specification. If we wanted to move towards exposing that information using the STAC specification, what the tool sets or libraries are out there? I looked at the STAC utils org, and there's some STAC server fast API and some node-based ones. But if we already have the backend, stored, what would sort of be our path forward there?
Yeah. And actually, so our STAC endpoint is based on STAC fast API. And so just for whatever that's worth. I'm actually Elasticsearch. I'm new to this STAC community as well. I do know, like, I've seen references to Elasticsearch. So I would, implementation found is, I don't know. I would recommend reaching out to that community to see what they're doing. It is somewhat new, so it's going to hit like 1.0. STAC is going to hit 1.0 like soon in the next week or two, hopefully. But it's a fairly new standard, and so people are figuring things out. But I will say it's been like a very welcoming community. I've been really happy engaging with them. So it's a good community to get to know if you think it sounds useful.
Hey, Tom, this is
okay. Yeah, I'll reach out. Thank you.
Hey, Tom, this is Rich Signal. I had a question about the STAC API there. So you have the entire Landsat collection too from USGS?
Mm-hmm. Pretty much up to like a month ago, because our dynamic ingestion isn't running yet.
Right. So, at USGS currently we use Amazon as our cloud provider, and but these notebooks basically don't use anything custom, right? For Azure.
Right.
So could we take the same notebook essentially, use your, I don't think we have STAC enabled either.
Yeah.
use your STAC catalog to do the query, and then like swap out the items for, is the pattern the same?
Yeah, I'm curious. Yeah, so the thing you would need to do is update the URL, the href on that. I'm going to try and get there. But yeah, like other than that, stuff should work as long as the STAC items agree. So like the items themselves, I don't know if we show it here, but it has stuff like the common band name, but also the projection information. As long as that matches, then it'd probably be fine. I'm curious if that would work. I will say, like, so we're working with STAC utils, I think it's STAC tools. So STAC tools is kind of like what we're using to generate our STAC items, and we're working with other trying to work with everyone to ensure that the stack items are identical for the same scenes that are hosted in multiple places.
Great. Okay, good.
I think there are a few other questions in the chat. If you,
Yeah. I'll try
if you
and
want
I'm
me to read it
scrolling
out.
up here. Yeah, so there's one from Micah. Will the planetary computer be in other Azure regions eventually? Maybe. If that'd be useful to you, let us know. The main issue is just cost. Like, these are big data sets. It costs a lot to host them. So what we've been doing so far is pushing everyone to West Europe, which is where all of our data is. But if that, that is a problem for some groups. So if it is a problem for you, let us know, and we'll add it to the list as another person interested in multiple regions. Yeah, there's a question from Emilio. Is there a predefined set of hub compute specs assigned to user approved? Yeah, no, there's not like a list of specifications. We're still trying to figure out what people want. Like right now we have like a small environment and a big environment, and it's like, is that useful? I don't know. Is it more confusing than it's worth? So we're still figuring that out. Yeah, and then there's a question here. There's an Google Earth Engine has an API for Python, R, and then the JavaScript definitely as well. We don't have great plans for that. So on our, currently we're working with some groups. We have an R environment. There's a really nice R stack API that works well. So we've made sure that that works with our endpoint. And we're trying to make sure that stuff works, at least for R. And if there's other languages, like, reach out to us. We don't want it to be Python specific, but the people who are working, like me, on the planetary computer, our background is in Python. And so that's kind of like our first focus, for better or worse. And then, we're definitely aware that like Dask is Python only. And so, if there were a great distributed computing option for R, we would kind of miss out on that, because, we're kind of pushing that into the user's domain, while providing a bit of hooks like the Dask gateway to make it easy to scale out. So, there's kind of a trade-off there. We're definitely prioritizing Python for better or worse right now, but we want to support other ones. Any other, let's see, there's one here from Joe. Do you plan to archive and provide AI ready data that can bypass stack search and loading data from cogs? Yeah, this is something we're trying to figure out, is to what extent we should like go beyond what like the like USGS, for example, is providing. Do we want like analysis ready products, or even making like our own? So you can imagine even something simple like we're looking at ghost data, and that's comes down every hour, I don't know, or so. And so it's kind of hard to work with as a time series. The data is fundamentally chunked by time as it comes in. And if you wanted to, say, look at a small region, do some time series analysis on a small region, that's kind of hard because you have to load data from so many different files. So we're like trying to figure out, would it make sense to offer like a roll up of ghosts that is chunked by space and merged by time, so that you can do really fast time series analysis on that, or taking it further to these like AI, stuff like that. I don't know. I don't have a good answer to that, but it's an interesting thing to think about. If you have thoughts, like, this would be a great place to talk about that.
I think that would be super useful for not only for GOES, but for a lot of the weather forecast products.
Sure.
That are currently distributed as like hundreds and thousands of grid files. Having that accessible as a like multi-dimensional, like 5-dimensional, ZAR data set would be phenomenal.
Yeah. So there's the issue of, is it feasible to store 2 copies of everything? It depends on the size of the data. Like, I don't think we can do that for Sentinel. Just too big. But for something smaller, then yeah, that's probably doable. But And then at that point, it's like, are we the right ones to do that? Or should the data provider be doing that? Maybe working with them. I know USGS is not well funded to do that type of stuff.
Unfortunately, yeah, no way either, right? So
no, sure. So I don't know. I don't know what the best answer is there. Is Stack evolving? Yeah, Stack is evolving. I think there are some API breaking changes, but they're finishing those up now as they reach 1.0. So there's some Stack items that might need to be regenerated, but the core stuff is like set. Like that's going to be fine. And then I guess one thing is worth mentioning, and I think you actually touched on it here, the Stack API. There's a Stack specification for like the actual items. I actually don't know if I showed it. API Stack V1 collections. Yeah, so here's an item from Sentinel, or a bunch of items. Like this describes what's in each of the files. The item specification is pretty set in stone. And then there's an API specification, which is like actually here, if I go to redoc, I think it's like, what endpoints can you hit? And what arguments do you pass there? And it's like that is more in flux. The actual API is more in flux. I think I got all the questions in the chat, hopefully.
Thank you so much, Tom. That was a lot of information to digest.
Sorry.
I think there's one more question. And in case if anybody wants to see some of the Q&A, I've tried to type it as quickly as I can at the meeting agenda notes. I think Hukwa has a question.
Okay, cost model for Planetary Computer. Yeah, we're trying to figure out how to explain this right now. So right now, so the Stack endpoint, like the metadata, what data do we have? That's free, public, anyone can access it. The data itself is also free, publicly accessible, with the caveat that we currently throttle data leaving West Europe, just because we are paying the egress charges on that data leaving West Europe. So we throttle that to keep our costs down. And we literally cannot charge people for that. In the future, if we do figure out how to do that, at that point we might charge for unthrottled data leaving West Europe. But within West Europe, Azure doesn't charge for data going from blob storage in West Europe to compute in West Europe. So that's also no charge. The trickiest thing is probably the hub. So like the actual compute, it's currently free. We're still, we're in private preview, private beta right now. So we literally, we're incapable of charging for this right now. But we don't really have a good idea for what this will look like longer term. That said, the hub is the easiest thing to swap out. It's much easier to swap out the hub than storing your own copy of Sentinel, for example. So there's projects like QHub and various other ones, Dask Cloud provider, that we want to work closely with to make sure that it's easy to do computing with the Planetary computer data from your own compute. Azure services, compute, and then the Azure services that I don't know if the question is that you're using or we're using. We're using AKS, Azure Kubernetes Service, blob storage for the data, one of the managed Postgres or Cosmos DB, one of the managed databases for the Stack endpoint, a few things like that.
Tom, is Microsoft, is Planetary Computer something they're kind of like see how you guys do for a couple of years and evaluate, or are they committed to it for, some longer period of time, or how does that?
Yeah, I'm not actually sure really, for like longer term vision. We're very careful about we don't want to say yes to like too much data too fast or things like that, because we really don't want to pull the rug out from people. If it ends up not being a thing, like we want people to be able to rely on this. And so that's why we want to figure out the story around the sustainability of the program itself. But that said, like, I don't have a great sense for what our like 5-year, 10-year plan is. But we want to do this for sure. Like, we're talking about it, we're thinking about it, but nothing concrete yet.
Well, maybe more importantly than that, even, I guess, and you already said it, is that you're helping to build out this open framework,
Mm-hmm.
and
Yeah.
And showing what's possible with this tooling, right, and
Yeah.
this approach, so that we can hopefully all, it's gonna lift all boats kind of deal.
Hopefully, yeah, hopefully.
Great. So, any more questions?
We have one more question that just came in.
Performance benchmark for working with different size of X-ray. 20 years of Landsat data. Let's see. So the again at the Dask Summit, I think it was Digital Earth Australia had a good talk on that. It was one of the earlier ones. Let me see if I can find it. Events. Anyway, I'll see if I can grab the link for this. But anyway, they had a really good performance. They had a good example. They were doing like a cloudless mosaic for all of Africa, or several of them. So they went into the details of how they did that. I don't know if this is visible or not, but let me put it in the chat. That might be, yeah, that should be visible to anyone, even if you're not registered for the conference. And then the videos for that will go up in probably a few weeks to the Dask or PyData YouTube channel.
Great. Okay. So no more questions? I think you already answered a lot of them. So another thing I want to ask for the last one is there is another option called application in that web page. What that used for, like on the Planetary computer?
Yeah. Yeah. So the various applications, like the idea, everything I showed here today was very focused on like, working in notebooks, coding, APIs, things like that. That's a small group of people who are working in sustainability. And so our hope is that these applications can be the thing that like broadens the reach of this. So we're working with other people in this area, like Carbon Plan, to do these, like the forest risk assessment, to put together these applications that can then be used by more people. That was really cool. And the what's it in the Pearl, I think the AI accelerated land cover mapping from Development Seed's really cool as well. It's a way to like refine, so take a pre-trained model and then refine it on new data and labels. So it's like a cool example of using Planetary computer data. In this case, they're using this data in the STAC API and then their own compute, their own GPUs, things like that to run this application.
Very cool. Thank you. Okay, so great. I think that's all we have today. So thank you so much, Tom, and everybody for joining us today. Cindy, do you have